This is the final presentation for Launch Vehicle Design 2's Group 2 Blue Oregano, consisting of Jack Korzienko, Christian Bookout, Jackson Treese, Grant Turner, Carter Davis, and Jacob Lee. The overview and objectives of our vehicle design approach. Blue Oregano as a company has a goal of developing, designing, and constructing a launch vehicle capable of sending up to 50 metric tons of uncrewed payload into low Earth orbit. Blue Oregano's mission as a company is to provide the world with a cost-effective and successful launch vehicle to aid in supplying future space travelers with goods that will enhance their quality of life. In order to achieve this goal, the team at Blue Oregano has begun work towards a new program coined Advanced Rocket Trade Enterprises, Mars International Space Station, or Artemis for short. The Artemis program will bring around a new launch vehicle designed to spark the beginning of the spacefaring trade industry. The new launch vehicle will be called Genesis 1. This launch vehicle will consist of 2 stages. These stages will be powered by liquid rocket engines, both Raptors and RL-10-Cs. These will provide ample thrust to get the vehicle payloads into orbit. The approach to this design was to maximize efficiency by minimizing mass and optimizing the ascent trajectory of the vehicle. The requirements compliance matrix for our company is relatively simple. There are 5 main requirements for the vehicle's compliance. The first being, the launch vehicle shall be capable of placing a 50 metric ton uncrewed payload into low Earth orbit at an equatorial orbit of a minimum of 800 kilometers altitude. This will be done as the first stage consists of 9 Raptor engines and the second consists of 7 RL-10C-1 engines. Each can produce approximately 2 meganewtons of thrust and gimbal, and each RL-10C engine can produce 102 kilonewtons of thrust and gimbal if necessary. Thus, both stages can provide the necessary means to propel and control the launch vehicle into an LEO orbit. The second is the vehicle cargo module shall be capable of docking with the NASA International Docking Adapter. This is successful in the fact that customers will be able to provide their own payload adapter and payload separating systems. To comply with the necessary protocols, payload adapters will be required to consist of major components of a payload separation ring, PSR, launch vehicle adapter, and a payload separation system. The third requirement is that the vehicle design process shall complete the design analysis and test flight stage no later than 4th quarter fiscal year 2036, and the design shall have a complete Gantt chart of the anticipated design, testing, and flight schedule. By meeting these testing and flight dates, the Genesis 1 shall be mission capable by fiscal year 2036. The Gantt chart incorporated later within this report ensures the progress of the Genesis 1's design and gradual completion. The fourth requirement is that the vehicle shall be designed such that current infrastructure can be utilized with minimal to no modifications. No standalone or new large-scale facilities must be constructed or built as a result of the design. In the Genesis 1's testing, development, and construction, it should not require larger scale facilities for the completion of this. The aforementioned abilities will take place in pre-existing NASA facilities and NASA-partnered corporations. Additionally, the Genesis 1 would be set to launch out of the Kennedy Space Center. The fifth and final requirement within this matrix is that the vehicle shall be designed to meet the human rating requirements in NPR 8705.2C and design constraints set forth by the Commercial Crew Transportation System certification requirements, dated 12/9/2010. The Genesis 1 follows the 4 functions of the Commercial Transport System certification requirements: validation of the technical and performance requirement standards, verification of the compliance with those requirement standards, consideration of relevant operational experience, and acceptance of residual technical risk due to hazards, waivers, and non-compliance. Moreover, all design pieces of the launch vehicle will be arranged so that ratification of the agreed milestone statement of work, contract requirements, engineering, and operational plans completed by the NASA program manager will be done ethically and swiftly. However, it was taken into consideration the fact that this vehicle is designed strictly as a cargo unmanned module, and therefore may not meet all of the exact requirements of the human rating during test flight.
On this slide, you can see a diagram summarizing our concept of operations. Our launch vehicle is going to start from Cape Canaveral, and its first stage is going to ignite with its 9 Raptor engines and climb to 1 kilometer altitude, fully vertical, and initiate the gravity turn maneuver with a 6.5-degree kick from vertical. After that, it's going to transition on its own um, from a fully vertical flight to a horizontal to achieve a proper orbital speed. Our max Q event is going to happen at around 78 seconds after ignition. We're going to be reaching 100-kilometer altitude at around 196 seconds. And our first stage main engine cutoff and separation is going to happen after 214 seconds after ignition. After that, we're going to initiate our second stage with 7 RL-10C engines, and we're going to be using its propellant to reach orbital speed and circularize the initial parking orbit with a burn that stops at 745 seconds after um, main engine ignition of the first stage. We're going to be using most of our propellant to get to the initial parking orbit, which is around 400, 500 kilometer circular orbit or close to circular. Once we are reaching that, we have done our simulation, and we're going to have around 20% of fuel left, the propellant total. And our final payload will be delivered to the target orbit around 800, 900 kilometer altitude with the leftover propellant. We have done our simulation that has proven that we have more than enough fuel left to reach our final destination, and we'll talk about this later in the sections after this.
As previously mentioned in the requirements compliance matrix, the human rating certification process is a NASA metric in which ratings are required for any vehicle on which humans may fly and is measured by the PLOC metric, or possibility of loss of crew metric. This spacecraft, however, is an unmanned cargo vehicle, purposed for the transportation of non-living material, and as such does not require a strict human rating certification for in-flight processes. If the Genesis 1 were to need a human rating certification, it will require moving through the NASA chain of command, including but not limited to the program manager, associate administrator for responsible mission directorate, technical authorities, and to the director of the NASA facility at which the certification is occurring. This is just to start the application, however, as to complete the certification, both the NASA administrator and associate administrator would need to endorse the certification.
For our cost analysis, we have assumed that the total available budget for the program is going to be 20% of NASA's yearly budget. According to Lembright, NASA was granted almost $20 trillion in 2019, and we assume that it will be granted at least that amount each and every year up to 15 years of while our program is still going. We're going to start in 2021, and the end of our development program is going to be in 2036, which gives exactly 15 years. And we have calculated that the total NASA budget for these 15 years, assuming 2.5% of inflation rate, is going to be $365 trillion. If we take 20% of that each year, just for inflation, we're going to have $73 trillion available in total for the entire program, which includes the development and testing and everything related to actually building the launch vehicle. We're planning to launch um, and build 6 vehicles to test all of the necessary systems and components. Each is going to be estimated, it was estimated to be 120 metric tons of dry mass. And that was used for our advanced mission cost analysis estimation, um, which has yielded a $33 trillion of total cost for our entire mission, which is under our available budget. So if there are any overruns, we should have plenty of space um, available to increase our actual funding and finish the program.
So this is our Genesis 1 vehicle fly sheet. For overall specifications, we have our total length for the vehicle at 94.62 meters, the outer diameter of the vehicle at 6.44 meters, the tank diameters of the LH2 tank, the LOX tank, and the CH4 tanks are approximately 5.8 meters, and the second oxygen tank for the second stage has a diameter of about 4.5 meters. We have a total thrust at liftoff at about 2.2 meganewtons per Raptor engine. Now we will have 9 Raptor engines on this vehicle and 7 RL-10C engines for the second stage. The entire vehicle on the pad weighs 91 tons dry with the 50-ton payload included, and 1,550 tons wet with the 50-ton payload included and all of the propellant. As far as overall vehicle layout goes, we have a payload fairing at the very top forward of the rocket. This will also house all of our communication systems for telemetry updates and stuff like that. Just aft of the payload section, we have the payload support structure. Now this will also house the avionics and RCS for the second stage. Just aft of the second stage oxygen tank, we have the helium supply for the second stage. And just after the LH2 tank, we have the second stage thrust structure, which houses all of the engine control systems for the 7 RL-10Cs. Just above the first stage LOX tank, we have the avionics for the first stage. Just below the first stage LOX tank, we have a helium supply for the first stage. And aft of the methane tank for the first stage, we have the thrust structure for the 9 Raptor engines and the engine control systems for those 9 Raptor engines, including engine gimbaling.
All right, so to begin our sizing process, we started by considering our total liftoff mass of the entire vehicle, because we needed to figure out the staging speed at which we're going to be separating the 2 steps. We have looked at the historical data, and it was quite clear that the structural ratio of around 0.06 for the first stage was reasonable, and that's what we have started with. On this slide, you can see the result of our gross liftoff mass optimization routine on MATLAB for different engine selections for both the first stage and the second stage. In the legend over here, you can see Raptor RL10. That's Raptor meaning in the first engine type, it's going to be the first stage, and the second engine type in the legend, it's the second stage main engine type, which those are also different, and obviously their fuel types. That was the primary deciding factor, is what type of fuel to select. So as you know, Raptor is going to be is using methane, liquid oxygen methane propellant. RL10 is liquid hydrogen oxygen. RD180 it's RP1, and so on. So we have looked at those different combinations, and on this graph you see the all of these curves represent basically the total liftoff mass in metric tons versus the staging speed of how much we are going to allocate our total mass towards first or the second stage. We have assumed that all of the drag losses, or at least the majority of it, coming from the atmospheric drag, is going to be absorbed by our first stage, and we want to essentially leave atmosphere just using the first stage. That's why even though with using this optimization, we have um, determined an optimal a minimum for the liftoff mass. However, we had to fix our um, staging speed to a much higher value. In this case, we picked 7 kilometers per second as our staging speed, meaning that the 7 kilometer per second is going to be provided by our first stage. And as a result, after all of the after the optimization, then the structural modeling, and then after incorporating extra losses and um, or extra components for especially for the second stage, our structural ratios were adjusted accordingly. So instead of 0.06, we see a structural ratio for the first step of 0.0651. And then the second stage structural ratio is much higher because it's less propellant, and it's more, and the payload itself is almost 50 tons. It's exactly 50 tons. So the structural ratio is 0.2647, as you can see here. So when we have determined our overall mass ratios for each stage individually, here are the results of the actual masses for each of the stage or steps in this case. So on the right diagram, you can see a rough draft of what is like how the entire stage is laid out and the relative sizes of the 2 tanks and their placement. This is assuming that we have already picked Raptor RL10 configuration. So our maximum liftoff mass for the entire vehicle is 1,550 metric tons. And the fully loaded first step is 1,398 metric tons with a dry mass of only 91 metric tons. That's just the first step. Out of that, the usable propellant mass is 1,307 metric tons of propellant, both liquid oxygen and liquid methane. Payload mass, which includes the upper step and the actual payload, is 152 metric tons. The entire vehicle was sized to the 6.44 meters outer diameter. Both stages have the exact same diameter. And the first step has 65 meters in its total height. We are going to be using 9 SpaceX Raptor engines as our main propulsion on the first stage, and which gives us a total thrust at sea level of almost 20 meganewtons. And obviously the propellant type is liquid oxygen, liquid methane for the first stage. The second stage, as you can see on the right diagram, it's much shorter, and then as you can notice that the propellant tanks are significantly smaller because it's far less the total fuel that we need to supply for the upper stage. It's only 75 metric tons of usable propellant, both liquid oxygen and liquid hydrogen. And we are using 7 RL10C engines for our upper stage, which gives us around 714 kilonewtons of thrust in vacuum. And again, since we're assuming our upper stage is going to be only operating in a vacuum of space, we're not considering thrust and any other parameters in atmosphere. And we have used our simulations to prove that, which we will talk later. Also, the diameter is exactly the same as the first stage, 6.44 meters, and then the total length or height of the upper step is around 30 meters. And the dry mass, excluding the actual payload, mission critical payload, is 27 metric tons. And obviously, we're delivering 50 metric tons of payload.
All right, next I'll be discussing the cargo module design of the Genesis. To begin with, the cargo module itself will be the second stage of the launch vehicle. Because of this, the primary and secondary propulsion systems will be the second stage systems themselves. Thus, meaning the primary system will be 7 ROTC engines, and the secondary system will be the RCS thrusters already attached to the second stage itself. Concerning the docking method of our cargo module, the cargo module will be utilizing an autonomous rendezvous docking capture mechanism, where this mechanism will be equipped with a wide range of electromagnetic spectrum-based systems, or in short, EM sensors. And the reason for the EM sensors is that these sensors allow the Genesis to detect and track its target spacecraft without any outstanding lighting conditions necessary. Additionally, they'll also allow the Genesis to filter any navigation position data in order to maximize the accuracy and fidelity of the trajectory onto these target spacecraft. Next, the equipment used for the EM-based systems are infrared cameras and LiDAR systems. And historically, the conjunction of these systems provided a maximized efficiency and accuracy of the component itself. Therefore, that's why we're utilizing EM-based sensors. Lastly, in order to maximize redundancy, the Genesis will also be equipped with RF communication sensors, and these sensors will be utilized only if the EM systems were to fail or provide a faulty trajectory analysis determined by the ground control team. And the RF sensors will be utilized where they will be able to target the spacecraft through GPS state differencing and relative GPS positioning. Lastly, in order to further maximize our redundancy of the cargo module, we'll be allowing the ground control team to manually dock our cargo module onto the target spacecraft. And if need be, a design robotic arm will be attached to the second stage in order to berth the vehicle to the spacecraft such as the ISS. On the top right picture, we see the cargo module where the cargo platform is displayed in the 3D rendering. And the bottom right, we see a NASA docking system, which is compatibly used for automatic, manual, and berthing docking mechanisms, which is just an example of how our launch vehicle will be able to dock onto the newly developed international docking adapter currently being developed by NASA.
So for the stage 1 primary propulsion systems, we have 9 SpaceX Raptor engines, each producing a thrust of about 2.2 meganewtons at sea level. These engines run on a full flow stage combustion power cycle that consists of 2 pre-burners, one that runs oxidizer rich and one that runs fuel rich. Their resulting plumes are sent through turbopumps to run the turbopumps for the fuel and oxidizer that feed them. The resulting oxidizer and fuel-rich mixture is then shot into the combustion chamber, where it is recombusted and sent through the bell nozzle, producing thrust. Each Raptor engine boasts an ISP of about 330 seconds. The total impulse per engine is 471.9 meganewton seconds. The propellant they run on is a methane liquid oxygen combination. So methane is the fuel and liquid oxygen is the oxidizer. And that runs at a 3.55 to 1 oxidizer to fuel ratio. The mass of each engine is approximately 1,500 kilograms, and the mass flow rate for each engine is 650 kilograms per second of total propellant. This propulsion system gives us a thrust to weight ratio at liftoff of about 1.25. On the right, you can see the arc deflection fan of the 5 gimbaling Raptor engines. So we do have 5 Raptor engines that gimbal up to 10.5 degrees to provide us with active stabilization and course correction. The dotted line surrounding each of the 5 gimbaling engines can show their maximum deflection to prove that there is no interference between them. For stage 2 primary propulsion, we are running 7 Pratt & Whitney RL-10C engines. Each of them boast a thrust of about 102 kilonewtons. They run on an expander combustion power cycle, so that consists of a fuel pump sending fuel down around through a heat exchanger on the nozzle that superheats the gas, and as it expands, it runs through a turbine, and the turbine then can power the fuel and oxidizer pumps. And then the fuel and oxidizer are then sent down into a combustion chamber where they're ignited and sent through the bell nozzle, producing thrust. This setup is highly efficient and has been proven very reliable for upper stage systems. That's why we selected it. They boast an ISP of about 450 seconds, so this is pretty top of the line for upper stage engine classes. The total impulse of each engine is about 56.15 meganewton seconds. And the propellant they run on is a liquid oxygen, liquid hydrogen combination running at a 5.88 to 1 oxidizer to fuel ratio. The mass of each RL10C engine is 190 kilograms, and they have a mass flow rate of about 16 kilograms per second. On the right, you can see that we have all 7 RL10s gimbaling up to about 8 or 9 degrees to assist in active stabilization and added attitude control. And you can see from the dotted line surrounding each engine that they do not interfere with each other.
In addition to main propulsion gimbaling, 2 secondary propulsion systems will be used on the launch vehicle to control it once it's outside of the atmosphere. The first of these are RCS thrusters. These will be used to control the attitude and trajectory of the rocket during orbital maneuvers or docking procedures. Below on the right is a diagram of a Gemini spacecraft RCS thruster. These bear striking resemblance to the thrusters which will be used on our launch vehicle, the Soviet 11D-428A. These thrusters are fueled with a nitrogen tetroxide and monethyl hydrazine mixture and can generate up to 130 newtons of thrust each. There will be 2 onboard RCS clusters on the launch vehicle, visualized in a top-down view in the bottom left figure. As you can see, having 2 of these allows for many degrees of freedom and attitude control. These will be controlled completely autonomously by the onboard guidance, navigation, and control systems. Additionally, several ullage motors will be placed along the outside of the upper stage, propelled by the liquid hydrogen from the upper stage fuel tank. These are helpful and important in the case of reignition in a zero-G environment. They allow to make sure that the fuel is concentrated on the bottom of the fuel tank during reignition procedures. As for solid propulsion, the launch vehicle Genesis 1 requires no solid rocket boosters and will have no solid propulsion systems on board.
Moving on to the tank pressurization. For the Genesis 1, the pressurization of the internal fuel and oxidizer tanks, currently containing liquid methane, CH4, liquid hydrogen, LH2, and liquid oxygen, LOX, has been decided as helium. The maximum assumed pressure for all non-helium tanks is 45 psi, or 310 kilopascals. Helium was chosen because of its historical proof from the space shuttle, and many other similar space vehicles, showing it to be relatively easy to handle and store in comparison to other compressants. These pressurization tanks are designed to be located in the space above the fuel and oxidizer tanks, in small groupings of 4 to fill the empty space that is located there. These tanks allow for a top-fed pressure control, as it has been shown as successful in reducing slosh in the past, especially when combined with internal tank rings to help reduce wall slosh.
So our structural design can be broken up into 2 stages. So for our first stage, we started the aft end of the entire vehicle with a thrust structure, and that contains all of the propulsion systems, the 9 Raptor engines, the propulsion control systems, the gimbaling actuators, and feed lines for the propellant for those engines. This structure also transmits all the loads from these engines to the entire rocket structure. So it's mounted to both the skins and the tanks inside. Also in stage 1, we have various support rings mounted along the body of every tank. This is to increase the structural integrity of the tanks and also provide a little bit of support for the skins. And they also all have cutaways designed to facilitate electronics distribution and propellant distribution. The inner tanks and inner stages for the first stage are reinforced with a couple added rings and added ribs to help mount systems such as the helium supply and avionics systems. For the second stage, we have a similar configuration with a twist. So we have the second stage thrust structure. So this is very similar to the first stage thrust structure, except it only has to hold 7 RL-10 engines and their propulsion control systems, their gimbaling actuators, and the feed lines for all the propellants for them. This thrust structure also transmits all of the thrusting load to both the skins and the tanks, the LH2 tank below. We also have various support rings that are housed at the ends of each inner stage that help align the tanks and also aid in mounting the skins and mounting various control things. They also have cutaways, just like in the first stage, to facilitate propellant feed lines and electrical lines at the rocket. In the second stage, we have added some H-beams for reinforcement so that the load isn't focused on the skins. These H-beams are mounted between the LH2 tank inner stage and the oxygen tank inner stage ring. So these H-beams help mitigate payload displacement and stress that are induced during the high acceleration maneuvers. These H-beams will also serve as great points of mounting for the helium tank supports and various other avionics control systems. As far as other structural components, we're using an orthogrid skin design. So you can see that on the right there. This design was chosen to decrease weight while also increasing structural performance and not losing structural integrity. Below, you can also see our full structural layout of the rocket from aft to forward. You can see where the inner stage skirts are installed and the inner tank skirts and inner tank systems and the aft and forward skirts as well. So we did 2 different analyses. One of them was a SolidWorks analysis on just the tanks and the inner tank structures. So these were missing all of the H-beams and tank support rings. And this proved that this served as a preliminary proof that our tanks would withstand the amount of forces that we put them under, up to like 1.5 times their rated pressures. And then we moved on to a full patch ran structural analysis. So we modeled this, the system in full and modeled every single support structure and surface as if it were in the real world, minus an idealization of the ortho grid as the skin. So the loads modeled during the structural analysis were inertial loadings in the vertical direction of about 6 Gs, and then inertial loadings of 1 G at 30 degrees from vertical, simulating a gravity turn. We also simulated skin friction at max Q, a payload mass loading equivalent to the inertial loading of 50 tons at 6 Gs, and an internal tank pressure of 45 psi. Now, here are the results for the displacement. You can see on the right, we had a max displacement occurring near the top of about 48 centimeters. That seemed like a lot at first, but then we realized that it was only about an angle of 0.27 degrees, and being a 95-meter tall rocket, it's very negligible displacement overall. So this simulation proved our worst case scenario, which would be max Q, max G, and a gravity turn all happening at the same time. In reality, that would not be in sync. Next, we have our stress in PatchRAN. So we plotted the stress pseudocolor you can see on the right. We saw that the max stress occurs near the bottom of the craft. This is expected, and that's only about 170 megapascals. So that gives us a factor of safety of at least 1.25 for tank skins and about 2 for all the other structures. Once again, this has performed excellently even in the worst case scenario.
One of our primary verifications of the vehicle and the fact that it's actually capable of performing the mission and delivering the required payload to the target altitude was our aerodynamic analysis coupled with the ascent dynamical simulation. So in this slide, you can see the result of our CFD analysis at various Mach numbers and altitudes. And on the right, this is just a snapshot of our aerodynamical model of a slightly simplified vehicle, but with all of its major components. And this is also, again, assuming that we are getting out of the atmosphere using our first stage only. Our max Q heating is only 282 degrees Kelvin, which is well below the melting temperature of aluminum, and it's only an increase of around 61 degrees of Kelvin, which was also backed by our theoretical calculations, which were slightly lower than that. The max Q is happening at around Mach 1.2 at an altitude of 10.34 kilometers, and the load experienced is only 0.87 of the gravity. And we didn't, of course, we didn't just make up those values. We developed our own ascent simulation. And on the but for that, we had to acquire a dynamical table of the drag coefficients and how it changes with the Mach number, as you can see on the left right here. And that's where we get all of the hour values for the max Q and then the total drag losses. And our max Q maximum drag was almost 0.5 meganewtons, as you can see right here. So our flight dynamic simulation was used to essentially simulate the entire ascent portion and then burn to the initial parking orbit. And it was all continuous, so it was including the staging, the gravity turn maneuver, also active throttling to limit the maximum acceleration that the vehicle is experiencing. So if human rating is considered, that would also be possible. It would be just a much harder limit on the acceleration. For this analysis, only 6 Gs of a maximum acceleration was considered, and barely any throttling was needed. We have used a higher fidelity atmospheric model up to around 100 kilometers. After that, it was just a simple exponential atmosphere, which helped to reduce the computational cost. But the result of this simulation, you can see on the right diagram, like with all of the events labeled with the exact timing of how they happen in the simulation, and their relative position along the downrange distance in kilometers on the x-axis, and then the height above the ground. So you see that there is a separation, and then both steps are initiated, and then the second stage is only burned for 745 seconds, which is, it's not burning all of its propellant. And it has around 20% of propellant left once we reach our parking orbit, which happens at around 450 to 500 kilometers, as you can see on this graph right here. To verify that we are actually staying in orbit after burnout of the second stage, we actually propagated our simulation for an extra 2 hours with no propulsion or anything. It was just the mass and everything remained constant, and we just looked at how the flight path changes with time to make sure that we are remaining in orbit and as close to circular. As you can see on this graph, it's not exactly circular, but it's as close as we could have done it without considering active control and engine gimbaling. Again, this is all considering only it only considers our main engines of both stages burning in the direction of flight. So we're not doing any engine gimbaling for this simulation. So obviously all of this can be optimized and even further reduced. But this is the worst case scenario. And in this worst case scenario, once we reach our second burnout at the parking orbit, we still have around 15.47 metric tons of propellant left for the whatever final maneuver we need to do to establish the final target orbit at around 800, maybe even up to 900 kilometers. That's what we consider as our margin of safety. That 15.5 metric tons of propellant, considering the dry mass and the payload mass, gives us almost actually about 800 meters per second of delta V. This was rounded down to make sure that losses are also accounted for. This is actually half or even more than, it's almost twice or more than twice what's needed for our final maneuver. If we considered, again, worst case scenario, a circular orbit at only 400 kilometers altitude, and that we need to reach a target orbit at 900 kilometers altitude. Again, our target is only 800 kilometers, and that would require only under 300 meters per second of delta V. As you can see, I mean, it's clear that even without any gimbaling and more advanced engine dynamical simulation, we're definitely reaching our destination.
All right, next we'll be going over the electrical system of the Genesis. To begin with, the main battery of the Genesis would be a lithium-ion polymer battery, and the specific battery would be Space Information Laboratory's 52 ampere-hour IntelliPack batteries. And the reason we utilize these batteries over traditional silver zinc batteries is that these batteries provide high energy density, they are small in size and weight, and they provide an advanced battery management system that outrivals traditional silver zinc batteries. Concerning TRL concerns of these batteries, it is important to note that Space Information Laboratory's battery has a TRL of 9 and should be moved and is mission proven and ready for launch vehicle operations. The reasoning for utilizing these reliable and power batteries is that these batteries will power and uphold the integrity of the guidance navigation control, health monitoring, communications, data acquisitions, and sensor systems of the Genesis. Moreover, these electrical systems will also be powered by the batteries during the umbilical interface, control command interface, and payload separation operations of the Genesis. Concerning the umbilical interface, this plays an important role during pre-launch and launch contact operations, where the electrical system will be signaling the ground control team the health of the vehicle, and if the launch vehicle needs to be stay on the ground or is ready to go, and operations can continue. Moreover, the umbilical interface will also provide opportunities to power the batteries on board the Genesis, and also plays in the provision of signal paths carried between the spacecraft and the ground support equipment system, which allows for pre-launch considerations of the health monitoring and during launch contact operations. Concerning control command interface, the electrical system aboard the Genesis also plays a key role during avionics. For the upper stage remote control unit, will be closely resembling the Alice 5 at a configuration of a 2A DC voltage nominally, and also be at most 16 commands with 2 master switches at any given time. It is important to note that this is an important factor during the avionics of the system. For the upper stage remote control unit, also will be closely working with the FTINU to provide accurate and detailed information for the trajectory of that launch vehicle. Concerning the payload separation, we'll be utilizing redundant pyrotechnic devices that are based off of the LS5 and Delta 4 Marmon type clamp bands. And these will be triggered and signaled by electrical systems through special separation detection circuits that will be located near the payload and adapter systems. It's also important to note that separation systems will be required to be single fault tolerant. Lastly, concerning the picture on the right, on the top right, we see the Space Information Laboratory's IntelliPack battery. On the bottom right, we see an Atlas 5 based block diagram concerning the power of the power-up system of the LS5, which will be closely used by the Genesis in our configuration of the power-up system of that Genesis.
Our launch vehicle will be equipped with a guidance, navigation, and control system to control orbital maneuvering and attitude adjustment mid-flight. This system is important to the success of the mission, and its automation will allow for the craft to make minor trajectory and attitude adjustments in flight to stay on the predetermined flight path. On the right is a simplified PID diagram of how the GNC system will control the attitude of the spacecraft. On the left, the desired trajectory and attitude predetermined is inputted and compared with actual sensor readouts from sensors on board the spacecraft. Once these are compared, an error is produced, which is fed directly into a PID system. This PID system is able to turn those errors into control signals, which are then fed to the RCS thrusters and the gimbaling on the main propulsion system. These then actuate to adjust the trajectory or attitude towards the desired, and the process repeats. There are two main sensors responsible for determining the spacecraft's orientation and position. The first of these is a star tracker. The star tracker consists of a camera which points out towards the starry night and is able to recognize patterns in stars to determine where the spacecraft is located and which way it is pointing. The second of these is an inertial measurement unit. This is used to track linear and rotational acceleration about any axis and consists of various accelerometers equipped onto a gyroscope.
The primary purposes of the communication systems on board the launch vehicle are to transmit telemetry data to the command center, as well as communicate with external satellites to track the location of the launch vehicle. The launch vehicle will utilize the Tracking and Data Relay Satellite System, or TDRSS. TDRSS is a communication signal relay system which provides tracking and data acquisition services between low Earth orbiting spacecraft and control and/or data processing facilities. This will be coupled with NASA's Near-Earth Network, a series of ground stations owned by NASA, commercial entities, and other partners that provide communications and tracking services to missions operating in the near-Earth region, including Earth-orbiting spacecraft. The current Tracking and Data Relay satellite configuration consists of 10 in-orbit satellites, distributed to provide near-continuous information relay to service missions. Together, these satellites provide data transmission on S, Ku, and Ka bands. The frequencies that the satellites operate on are shown in the table here. The communication equipment located on the launch vehicle will be located in the second stage, with video cameras located in positions throughout the launch vehicle. There are 4 S-band PM antennas located on the fairing of the launch vehicle. The S-band PM system is responsible for transmitting information to or receiving information from the ground or the TDRSS. There are 2 S-band FM antennas located on the launch vehicle. The S-band FM system is responsible for transmitting data to the ground stations. There is 1 Ku band antenna located in the payload bay that is responsible for communications with the TDRSS when the payload is being deployed and for radar operations. The radar portion is used to skin track satellites or payloads in orbit to facilitate a rendezvous. Finally, there are 4 L-band antennas located on the fairing of the launch vehicle. These communicate with the 2 Flight Termination System units and are responsible for communicating with GPS satellites to determine the location of the launch vehicle.
All right, next we'll be discussing the health monitoring system of the Genesis. The health monitoring system of the Genesis will play a critical role in the success and integrity of our launch vehicle. Moreover, it will provide the means of improving aspects of our vehicle over future iterations. To begin with, the Genesis would be equipped with a dedicated network of fiber optic sensing system sensors, or FOSS sensors for short. These FOSS sensors were able to detect pressure, temperature, stress, strain, and vibrational changes throughout the launch vehicle. The advantage of utilizing FOSS sensors over traditional strain gauges and or pressure transducers are the increase in sensitivity and reduction in size and complexity. The FOSS sensors also take advantage of fiber gratings and grating techniques that accurately detect changes in vehicle parameters. Two sensing system techniques that take advantage of fiber gratings are cryo-FOSS and high-FOSS. Cryo-FOSS is a special technique of cryogenic liquid level sensing that we utilize within the fuel tanks and fuel pumps of the Genesis. These sensors will be able to accurately measure cryogenic fuel levels with high precision and accuracy and notify the ground team of the Genesis fuel status during all times of operation. The high-FOSS technique is also a very accurate method. This method will utilize traditional wavelength division multiplexing and optical frequency domain reflectometry in order to detect high-frequency vibration changes throughout the vehicle. This method would be utilized within high domains of pressure and where during max Q moments where vehicle telemetry is very critical to mission success. Lastly, concerning stress, strain, and pressure, the FOSS sensors will act as stress and strain gauges and pressure transducers and accelerometers and will be placed within the stage joints and fuel tanks of the Genesis. Lastly, the data handling system is a very critical component for vehicle parameter telemetry for the vehicle. In order to accomplish this, a data acquisition system based off the Atlas V will be used on the Genesis. The data acquisition system will be able to read all of these vehicle parameters detected by the FOSS sensors and provide the ground control team with a clear status update of the Genesis at all times of operation. The importance of the data acquisition software system will also be that it will also read data coming from the fault-tolerant inertial navigation unit and provide guidance navigation control parameters to the ground control team as well. Above all, the importance of the health monitoring system is critical to mission success. This is so for the health monitoring system will allow for further understanding of the structural performance of the Genesis throughout its mission life cycle and allow for increased capability of structural parameters over future iterations. On the top right, we see the strain gauge versus FOSS sensor sizing and their applicability in vehicle parameters. On the bottom left, we see the cryo-FOSS technique. In the bottom right, we see the high-FOSS technique.
The launch vehicle will utilize the Autonomous Flight Termination System, developed by NASA. This independent, self-contained system uses redundant flight processors that track the launch vehicle's location using GPS and IMU navigation sensors. The software has configurable rule sets that are uploaded pre-flight, and should the launch vehicle trigger one of these conditions, the AFTS will terminate the flight automatically. This system has been proven on other launch vehicles as reliable, and the flight software, called the Core Autonomous Safety Software, has been approved for operational use at both the eastern and western launch ranges. The system will use 4 independent flight processors housed in the second stage in 2 separated hardware units that receive input from GPS and IMU navigation sensors. The system also utilizes L-band and S-band antennas, a vehicle battery, and a power distribution box. All of these systems will be commercial off-the-shelf hardware. In the event of the AFTS terminating the flight, explosive charges lined on the propellant tanks will detonate, igniting the propellants and destroying the launch vehicle. Testing for the components of each system is scheduled to take place as soon as fabrication of the components allows. This testing will continue throughout the fabrication process, testing each major addition as they are fabricated until the final complete system undergoes testing. Once all components have been tested, the final structural and interoperability tests will take place, with the flight termination system tests being the final tests before flight testing. The flight test period is scheduled to start in 2032, just after the flight termination system testing is completed. This time frame was selected because all fabrication of the launch vehicles, as well as the all component testing, will have been completed. 2 test flights are scheduled to take place, one in 2032 and the other in 2033, as well as a 2-year period of post-test analysis following the first test. This allows for any issues discovered during the first test flight to be corrected and tested on the second flight. Should no problems occur on the first flight, a second flight will still be conducted to ensure reliability.